We will very briefly touch upon the hardware upheaval caused by the Manycore processors and the software shortfall in terms of exploiting the parallelism and performance of the Manycore processors. We introduce a new computing model that exploits the parallelism and performance by overlaying a signaling architecture on top of the von Neumann serial computing model. The resulting managed Turing machine network supports the genetic transactions of replication, repair, recombination, and reconfiguration. We show that this provides the architectural resiliency of cellular organisms and improves availability, reliability, performance, and security. We apply this model to a service platform to demonstrate self-repair, auto-scaling, live migration, and transaction security of applications written in C, C++, and executed in a new OS called the Parallax OS. We will show a demo. We conclude this presentation by some observations on future research. I recommend von Neumann's Hickson lectures for many insights on which our results are based upon. The new computing model is discussed in the book Designing a New Class of Distributed Systems by myself. As is being emphasized in this conference, the Manycore server is indeed causing an upheaval with its parallelism and performance. The 32 core and the 48 core microprocessor chips are causing a discontinuity in the. If you are a bellhead like I am, it is easy to imagine an architectural transformation of current data centers from their current role of resource management to services switching. When you have hundreds of or even thousands of cores inside a server with high bandwidth connectivity, much of the current generation server, networking, and storage infrastructure with their server-centric and low bandwidth origins become obsolete. Who needs fiber channel switching? Does TCP/IP communications make sense inside the enclosure? Do the current operating systems with their lock-based implementations scale inside the enclosure? So we can envision a new architecture where the big servers operate as clouds and the switching architecture is completely optical. If server is the cloud, then what is the obstacle? Current distributed computing models have evolved from their server-centric and bandwidth-limited network architectures. The von Neumann serial computing model is essentially a node-centric computing model and is not ideal for a network-based computing. It mixes both resource management and service execution in a serial fashion as shown here. And a network of nodes essentially have evolved into a web of complex management systems that manage end-to-end distributed transactions. There are two problems with this approach. Number one, end-to-end transaction response time is no longer controlled by the node operating system. The transaction resiliency requires network-wide resolution of contention for resources that impact the transaction based on workload fluctuations, business priorities, and latency constraints. Current management strategies provide no easy visibility and control of end-to-end transaction management and therefore lack the telecom grade trust. This picture shows the von Neumann stored program control solution with single core. When the instructions are executed, you get a fixed single behavior. With multiple cores and multi-threading architectures, the same CPU with multiple cores can provide runtime multiple I/O behaviors. Now we introduce a parallel management signaling network to provide multiple behaviors for the management also. Here we show the 4 cores converted into self-managed elements with signaling capability and provide OS FCAPS, fault configuration, accounting, performance, and security management. The parallelism of computing and management workflows allows the dynamic update of the computing workflow characteristics and thus bring the cellular resiliency into the computing architecture. This picture shows 3 servers with Parallax OS, each with 2 cores converted into dimes. A runtime orchestrator running in Linux provides the workflow execution across these servers. The proof of concept demonstrates creating a dime network, discovering the nodes and the cores, and creating dime applications with their management profiles and executing them. Various features such as I/O redirection, fault management, and live migration are also demonstrated in this demo.
This is the overall system we'll be using for the Parallax proof of concept demo. We have 2 desktop PCs as well as a laptop. The desktop PC on the left is a Pentium D. The desktop PC on the table is a Core 2 Duo. These machines have no hard drives as we'll be booting them up via Pixie. The laptop is our orchestrator. It is currently running Ubuntu Linux. We'll go ahead and start the power up on these machines. We'll also verify that there is no hard drive inside this machine. All we have installed is the network card, which it will be booting off of, as well as the video card. We'll turn on the power to that one as well. You can watch the operating system boot on the Pentium D. Boot up is very quick. Parallax was written from scratch in assembly, so the operating system weighs in at about 16 kilobytes. That one's complete. And we'll just wait for the Core 2 Duo. And that one is complete as well. So we will take the orchestrator machine and we will actually start up Parallax. Parallax runs in the background on Linux, and if we start up a web browser, we can get into the Parallax orchestrator and see the machines that are currently available. Within the Parallax orchestrator, we're given an overview of the current system. Nodes represent physical boxes, and the dimes within them represent CPU cores. In this situation, we have 2 physical boxes with 2 cores on each. The various icons within the dime allow us to distribute a program, adjust the FCAPS parameters, see current information on the dime, and also start and stop the execution. You can also see logs of the overall system as well as logs of the dimes themselves. You can see here during discovery we found our 2 nodes and also get some basic information on what they currently have. An interesting aspect of Parallax is its ability to send input and output to other dimes based on system parameters. These interactions require no program changes as it's built into the core functionality of the operating system. I'll demonstrate this with a simple program that runs a counter and displays its output on the screen. We'll distribute the program to DIME 1 on node 1. We will also modify the FCAPS parameters, in this case configuration, with the output redirection set to itself. And then we will start up the execution. We can see that the program is running on node 1 DIME 1, and it is currently displaying the counter. What we will now do is, while the program is running, we will change that configuration to point the output to a different DIME. In this case, we'll be using it to send to the other machine. You can now see that the output is being displayed across the wire, and the counter has stopped on this machine. The program is still running on node 1 DIME 1. However, we've changed it to redirect its output to node 2 DIME 1. Again, no changes have been made to the program. These are operating system parameters, so no program changes are needed. In fact, this program is just printing to the screen like it normally does, and the operating system is taking care of where it actually gets distributed to. We'll go ahead and send the output back to itself, and we can see it catches up where the display left off. We'll switch gears now and take a look at a virtualized Parallax environment. We have 2 virtual Parallax nodes, each with 2 cores each, so in effect we have 4 DIMEs total. Take a look at the screen on one of these Parallax nodes, and we get some basic system information. CPUs, we see that there are 2 cores here. They're not flashing, so they are idle. We have memory usage, network transmit and receive, real-time clock pulse, and also we can see which of the nodes and DIMEs we are currently on. This is node 2, and we are currently looking at DIME 1. Parallax supports virtual consoles for each of the CPU cores, so using the F function keys we can toggle between the different DIMEs. If we start up a program, let's say this one here, and execute it, we can see that it displayed, and we can also switch between the consoles to show that that information is only on DIME 1. Take a quick look at the failover capabilities. We'll start the counter application. This is a very simple program that just runs a counter, but it also updates the orchestrator with its current state. We will change the fault parameters and give it basic fault tolerance. That's complete. And now we will simulate a hardware failure by turning off this machine. And we should see the orchestrator redistribute the program and also its state. So it left off more or less where it was before. The orchestrator is only getting details from the application every 5 seconds or so, but the proof of concept works correctly.